going to start our unit on exponential and logarithmic functions. All right. I don't know if you made it all the way into this unit last year in Algebra 2. If you did, it will be a review. If not, no worries. I've got you. We're going to go through this. This will be our last unit, focusing just on algebraic concepts. When we return after our Christmas break, we'll be getting into the world of trigonometry. So for us to gain a clear understanding of how an exponential function behaves, we're going to focus on this basic one, and I want to compare, because you spent so much time in Algebra 1 and Algebra 2 on linear functions, right? So I put this basic linear function here next to it, and this is going to be one of our basic exponential functions. And the key recognition you're looking for when you're doing this is in exponential functions, your variable is going to be in the exponent. So if you look at the one here, it says 2 raised to the power of x. So your variable is in the exponent. That's why it's called an exponential function. So if I were to just use these basic x values, around the origin, all right, I'll start with a linear since that's what you're used to, right? 2 times negative 3 is negative 6. This is negative 4. Negative 2, that's 0. That's 2. 4, and 6. All right, so you'll see that it has a constant rate that we're increasing, right? That's called the slope. When you do exponential, I'll start with 2 to the first power, right? 2 to the first power is 2. 2 squared is 4, and 2 cubed is 2 times 2 times 2, which is 8. Anything to the 0 power is going to be 1. And then if you do 2 to the negative first power in your days in algebra, right, you actually write this as 1 over 2 to the first power, which is 1/2. Same idea with 2 to the negative second power. That's 1 over 2 squared, which is 1/4. And then lastly, 2 to the negative third power is 1 over 2 cubed, which is 1/8. Right, so you can see that as we're moving to the left, right, if I were to plug in -4, -5, -6, as I'm moving to the left, I'm going to get smaller and smaller and smaller and smaller, but I'm never actually going to hit 0. Okay, so when you look at this first one, right, exponential growth, so this is exponential growth, refers to the original value from the range increases by the same percentage over equal increments found in the domain. For linear growth, right, so linear growth refers to the original value from the range increases by the same amount. Right, like in the previous one, that amount is 2. All right, so this is significant, right, for exponential growth over equal increments. The constant multiplicative, right, you can see we're multiplying by 2, or in the case of getting more negative, dividing by 2, right, getting smaller. All right, but in terms of the linear growth, then this is called the additive rate of change because you're just continuing to add or subtract 2 from each value. All right, so it may not make a huge difference when you're focused around the origin, but obviously as you move further away, it's going to be a big difference. All right, so let's graph that first example we just did. So I'll fill in the table again, right? This is 1/8. Let me zoom in. This is 1/4, 1/2. That's 1. 2 to the first power is 2. 2 squared is 4. 2 cubed is 8. So if I were to plot these on this grid right here, my y-intercept is 0, 1. Then I have 1, 2. 2 squared is 4, and 2 cubed is 8. All right, so that growth is obviously, since we're multiplying each time by another 2, it's going to increase very rapidly. Then this is 1/2, 1/4, and 1/8. So we're going to get closer and closer to the x-axis, but never actually touch it. All right, so something like that. All right, and so this is one of your basic graphs showing exponential growth for 2 to the power of x. Now, there's some characteristics here. I'll kind of zoom in here, these characteristics. You can see that our domain is all real numbers. Plug in any number you want, no issues there. The range is not all real numbers, right? As I said, we're not going to get, we can't get negatives, and we're not going to be able to hit 0, all right? So that's why the range is 0 but not included, right? A parentheses there to infinity. You can see as we move to the right forever, the function is going towards infinity. As you move to the left forever, the function is approaching 0 but never touching it. The function is always increasing, going from left to right. We're increasing the entire time. That's why it's called exponential growth. All right, and we have a asymptote, horizontal asymptote at y equals 0, which is the x-axis, which is why we can never touch it, and the y-intercept is 0, 1. All right, so that's kind of your basic exponential function. So here's the form we're going to focus on today, right here. F of x equals a, which is some starting value, all right, your initial value, times your b base. And we're going to put some limitations on this. Our base is always going to be positive. All right, it's going to be between 0 and 1 would be what we call exponential decay. All right, so it's going to be decreasing the whole time. And then if b is greater than 1, like we just saw with b being 2, then it's going to be exponential growth, so increasing the whole time. All right, so b will never be 1, which kind of makes sense, right? If you take a base of 1 and raise it to any power, 1 squared, 1 to the 5th power, 1 to the negative 3rd power, it doesn't matter. Those will always be 1. So not really anything fun is going to happen when your base is 1. So that's why we have those restrictions. So if we just take a look at these, right, these 4 functions here, this first one is a quadratic function. So it's not exponential. This one is, right, you notice the exponent contains my variable. This one is a linear function, so not exponential. And then this one is also exponential because it has our variable in the exponent. So just a quick little blurb here about why we put those limitations on there, just because we can't have those bases that other than positive bases that would make an issue in terms of having things that are not real numbers. And then, as I mentioned before, bases of 1 are extremely boring, so that's why we don't do that. So let's go ahead and do some evaluation, something that hopefully you will remember from last year. So I'm going to plug in 2 and evaluate this without a calculator. So 2 plus 1, so that's going to be 5 times 3 raised to the 2 plus 1 power, which is cubed. All right, don't forget your order of operations. You do 3 cubed first to get 27. And then let's see, 5 times 27, 5 times 30 is 150. Minus 15 is going to be 135. All right, let's do this next one, but we're going to use a calculator. So f of 3, so 8 times 1.2 raised to the 3 minus 5 power. All right, so simplifying that, you get 1.2 raised to the negative 2nd power. So it says to use a calculator, so I'm going to go ahead and use Desmos to figure out what this is going to be. It says to round to 4 decimal places, so I'll go ahead and do that. But usually I just round to the nearest thousandths place. So we have 8 times 1.2 to the negative 2nd power. So you can write it as 5.5556, or really this is 5.5 repeating, or you can write it as a fraction 50 over 9. Your choice. It does say to round using decimals, so I'll go ahead and do that. I'll follow the instructions and write 5.555, and then that would be 6. All right, so there's a quick kind of review of some algebra with exponential functions. Okay, so as I mentioned, we're going to be focused a lot on exponential growth first. All right, so the only thing that makes it exponential growth is that your base, your b base, is going to be greater than 1. Right, that's it. If your base is between 0 and 1, right, so most likely to be a fraction that's between 0 and 1 or a decimal, right, then that's going to be exponential decay. So all that does means is that you're going to be decreasing the entire time. So if we look at these 2 examples about population, which is one of the most common applications of understanding of exponential functions, we have our function says the population at time t, which is in years since 2013, their initial amount of population in India in 2013 is 1.25 billion people. We're increasing, right? So this is, you'll notice my rate is greater than, or my base is greater than 1. So we're increasing at a rate of 1.2%. So how they got that was they did 1 plus 0.012. All right, so that's how they got 1.012. And that's raised to my power of t. And we want to figure out, okay, if we know the population in 2013, and we think we know what the growth rate is going to be yearly, then we can plug in to this exponential function to essentially approximate what we think the population will be in 2031. All right, so since it says years since 2013, right, that would mean 18 years from now is 2031. So I'm going to plug in 18. So 1.012 raised to the 18th power. I'm going to go ahead and use my calculator to figure out what this is, and it wants me to round to the nearest thousands place. All right, so we have 1.25 times 1.012 raised to the 18th power. So 1.549 billion people. 1.549 billion people. That's what we're expecting to happen in 2031, right? Since we don't actually know, right? This is hopefully what happens, but we're not sure. If our model is quote unquote good, then we'll be close. All right, let's do the same idea, but with a different country, with China. So we have our exponential function is being modeled with 1.39 times, right? And again, how they got this is they took 1 plus the rate of 0.006 to get that 1.006 number, right? That has to be greater than 0, or excuse me, greater than 1. Otherwise, it won't be exponential growth. So based on this, right, if I just look for a second, if you look at the first number is 1.25, right? I know it doesn't feel like a lot. We're talking about billions here. So this is a very big difference. So 1.25 billion people in India in 2013, 1.39 billion people in China 2013. So China is starting out with a lot more people. But if you look at their growth rate, China is only growing at 0.6%. And the growth rate here was actually 1.2%. All right, so literally double in terms of that rate. Right, so we're going to see what happens when you have a lot more people to start, but your growth rate is not going to be growing as fast. So let's plug in the same thing because it's years since 2013, so 18 years from now for 2031. All right, and so this is going to be, so changing my numbers in my calculator. All right, so 1.39. And this is 1.006. So we get 1.548 billion people. That we expect in 2031. So if you look at this, it asks us to just take a moment to compare between these two countries for what we expect to happen in 2031. It's not really that far off, where we're talking about off by a thousandths place, right? Which is, it's not nothing. We're talking about billions here. So even a thousandth of a billion is still many people, but it's relatively close in the grand scheme of things. But you can see that how we got there is different, right? India is essentially playing catch up in its growth or in its population, but it's growing at a faster rate. So over time, it will eventually catch up to the population in China. Okay, let's talk about how to write or find exponential functions if you're given some information. So the first thing I always hope, right? I always hope I'm going to get this point, right? Where it's what I always quote unquote say year 0 or the initial value, because that would just give me a right away. So let's just look at this example with the wolves. It's saying that in 2011, 129 wolves were counted. All right, so we're going to model this situation over time t since 2011. So my year 0 is 2011 when I had 129 wolves. Okay, so 2 years from now, in 2013, the population is 236 wolves. So again, because they gave me my year 0, that gives me my initial value for A. So if this is the number of wolves at time t is A times B raised to the power of t. I actually already have that A value. It's 129. That's the starting number of wolves. Okay, and I'm going to use my other point. Right, 2 years from now, there will be 236 wolves to solve for my time t. All right, so I'm going to plug in 236, that's the number of wolves 2 years from now, equals 129 times b, I don't know what b is, raised to the t power, which is 2, right, 2 years from now. So this is, I can solve this. Divide that 129 over there. So we get divide 129, right? And then I'm going to take the square root, right? Because I don't want b squared, I want b. So my b is going to be, and I'll go ahead and round once we get it in the calculator, the square root of 236 over 129. So the square root of 236 over 129. So my b is approximately 1.353. So 1.353. So to write my actual model here, I have n at time t equals, remember 129 is the initial number of wolves times our rate, all right, of 35.3%, but we add 1 raised to the power of t. All right, and you can use that from now, right? If you wanted to know, okay, how many wolves do I expect in 2015? Now you raise it to the 4th power. All right, so it's how many years since 2011. Okay, so the second one is a little bit different. You'll notice the first thing I see in these points is neither of my points have an x value of 0. So that means I'm not given my initial value. So what you're going to do is you're going to write 2 separate equations using both of these. All right, and then we're going to use our understanding of solving linear systems. I know these are not linear equations. But we're going to use that same understanding of solving a system to figure out what a and b are. Okay, so in this first one, when I plug in 1 to x, so f of 1 is 3, I raised to the 1st power. Okay, in this one, when I plug in 2, so f of 2 is 4.5, I b raised to the 2nd power. This one here on the left is a little bit more straightforward because it does have b to the 1st power. So I'm going to say that my letter A, all right, my letter A is equal to 3 over b. All right, and it's okay if you chose the other way, if you wanted to say that b equals 3 over a. It really doesn't matter, right? It will solve whatever one you want. It shouldn't matter if you do your algebra correctly. So if I look on the one on the right and I substitute, right, if I take this letter A and I replace it with what a is equal to over here from my other exponential equation, I'm going to write this as 3 over b times b squared. Going to your days in algebra, right, when you have b squared divided by that b, that's going to be 3 times b to the 1st power. All right, and if you divide both sides by 3, 4.5 divided by 3 is 1.5. So there is my b. Now, like when you did a linear system, once you find one of them, you can use this same equation over here to find the other one. So I'm going to write a equals 3 over b, which is 1.5, and 3 divided by 1.5 is 2. All right, so when I write my answer, I'm writing it down as 2 is my a, and then times my b, which is 1.5 raised to the power of x. All right, so that's probably something you've never done. Even if you did this unit with your Algebra 2 teacher, you probably didn't do a question like this, but just again, using your algebraic understanding to help you find it. Okay? All right, so let's talk about using a graph to help us do it. Same process here. The first thing I look at is this point here, 0, 3, right? And again, that's going to be 0, my a value. So I like that because I've already found a. Looks like another point it goes through could be 1, 6 or 2, 12. I'll use 2, 12 so it's a little further away, but again, 1, 6 should be okay when you're doing this. So I'm going to write down f of x equals my a value of 3 times b to the power of x. So I know my a value. Now we're saying if I plug in 2, so if I make x 2, so if I make x b squared, all right, then my f of x, my y value, is 12. So if I move that over, right, this says 3b squared, divide by 3, you get 4 is b squared. But I don't want b squared, I want b. So b is going to be 2. Again, if you go back to your days in algebra, right, when you take the square root, which we just did, you should be thinking about plus or minus. But because I told you at the very beginning of this lesson that our bases will always be positive, that's why I have not been using and will not use for this unit plus or minus when I do that algebra. Okay, so my answer for writing the exponential equation, right, don't stop there, is going to be my a value, 3, times my base of 2 raised to the power of x. All right, so that's it for that one. Okay, so now let's move into some applications, and probably the most common application for exponential functions is looking at compound interest with maybe your investments or with loans, or we'll even talk about looking at the very end, talking about decay of chemical substances, like things like that. So that's going to be your most common application here. So with compound interest, right, so what we're looking at here is we're saying that we look at the compounding, which is just essentially meaning that you're earning interest, or I guess could be the other way. We're talking about your loan that you took out, right? The bank is asking you to pay interest not just on your original value, but on the amount that's accumulated each time. So that's why it's called compounding, because it literally just continues to build on itself. Okay, so we use this formula here for our compound interest to calculate it, and I'll kind of go over with you what all this stuff means. A of t is the amount at time t, and we're measuring t in years. P, that capital P, is the principal or the initial investment or the initial loan amount or the initial population, whatever it is, the initial thing, starting value. R is the rate, and they will give you that rate. Letter N is the number of compounding periods in 1 year. So if you're talking about, there's a little table here at the end, or right here. We're talking about compounding annually, that's once a year, semi-annually, twice a year, quarterly, 4 times a year. So, this is a really good table to kind of memorize for yourself. And then obviously time t measured in years. Okay, so this is a formula that you'll be using so much, you should hopefully have it memorized. So let's write it down. The amount at time t is our initial amount times 1 plus the rate over the number of compounding times per year raised to the n times t. In this case, I want to figure out the amount, and I'll just write down the formula here. If I invest $100,000, wow, that's a lot of money, times 1 plus my rate of 0.12, make sure you write it as a decimal, divided by, all right, the number of compounding times per year. It's saying compounded weekly, and we're using 52 weeks in a year, raised to the 52 times t power. So this is the model. Some teachers will have you simplify the 0.12 divided by 52. Go ahead if you want. There's no real reason to do that. But now we're going to use the model by evaluating this at 30 years. So essentially 30 years from now, what can I expect if I don't touch it and get this interest rate of 12% compounded weekly? So every week my money is going to make money on itself, which is super nice and not actually something that happens in the world. But that's okay. Let's use our calculator. All right, so I have $100,000 is my starting value times 1 plus my fraction of 0.12 over 52 raised to the 52 times 30 years. Okay, that's my power. So I'm expecting in 30 years, based on this model, this is amazing. I initially invest $100,000 and my return is over $3.5 million. Gosh, what a world that would be. So $3,644,675.88. Right now, obviously, this is an extremely simplified problem. And again, as I mentioned, no one ever gets compounded weekly. That would be absolutely amazing. Usually, you get compounded monthly in a typical one. And also, right, we're talking about never touching your investment. The volatility of the stock market, you're never going to get 12% interest, right? They say your expectation over the 30 years of investing would be to hope to have an average growth rate of 8%. I'm talking about over the entire life of the 30 years, not 8% a year, right? Some years would be better than others, right? That's just the cycle of the market. Okay, let's talk about a 529 plan. This is extremely, what's the word I'm looking for? This is something I identify with, right? I can relate to this because I have 529 plans for all my children. I know I joke all the time about picking my favorite child, I won't say the name, but picking one child and sending that child to college, since college is extremely expensive, as you guys know or will find out very soon. But 529s essentially allow you to invest money for your child's future tax-free. So you don't have to pay taxes on it until you actually start using it when they turn 18 or whatever year they start to go to college. Okay. Now, the thing about it is it can only be used for educational purposes. You can't all of a sudden be like, oh, I'm not going to college. Here's this money that I've been investing. I'm going to go ahead and use it. It can't. It has to be used for educational things like room and board, tuition, books, things like that. So in this case, we got Lily wants to open up a 529. So let's write down the stuff we know. We know actually we're solving for our initial value. She wants to know how much does she need to invest now. So this is the starting value we don't know, times 1 plus our rate, which is going to be 6%. So 0.006 compounded semi-annually, so that's twice a year, raised to that n times t, so 2 times t. So we're saying in 18 years, so the amount at 18 years, she wants to have $40,000 for her granddaughter, all right, which is super nice, Grandma, but not going to go a whole long way with how expensive college is going to be when your granddaughter is ready, times p, or equals p times 1 plus 0.06. Again, if you feel the need to divide that, feel free. And then I'm going to plug in 18 for my years. All right, so we're going to actually solve this for p. So essentially, if I find all that stuff on the right and divide it by 40,000, that will give me how much Lily's grandmother, I guess I should say Lily is the grandmother, how much Lily should be investing today. So let's see. Let's do 40,000. And I like to do it in one step, but feel free to do it in multiple steps. Just try to wait until the end to round, over 1 plus, and this is 0.06 over 2. Oops, I already had that in there. 2 raised to the 2 times 18 power. All right, so we're saying that according to this model, Lily should enter her nearest, whatever bank she uses, or go online and deposit in this 529 account $13,801. Now, just from someone who does invest, and if you invest, you probably understand the same thing. No one's really investing, $13,801. They'll probably invest $13,000, maybe $10,000, maybe $13,500. It's rare to pick that number, right? This is just an idea of what Lily would need to head to the bank or online deposit now into a 529. Okay? All right. Let's move into our last application of this. We talked about annually, semi-annually, quarterly, monthly, and we stopped there. But if you were to keep going and you were compounding daily, so every day you're multiplying your money on itself, which is really good for your investments. Again, not a thing that happens. If you were to compound hourly or every minute or every second, what happens is you start approaching a certain number, right? You can see these last few numbers here, right? These last few numbers are approaching a number that we call 2.7183. All right, and this is something that was discovered in the 18th century by a Swiss mathematician named Leonhard Euler. All right, and you notice his last name starts with the letter E. So as any mathematician with any ego, all right, no pun intended there, any ego has, he decided to use the letter E for this number. So this is how the number E was discovered. So approximately 2.7183. In terms of the characteristics of it, it's similar to pi, and that is an irrational number going on forever. But we use it in terms of our whenever we see compounding continuously or continuous growth, or when we do exponential, or I should say half-lives and radioactive decay, you'll get that letter E. Okay, so in this case, it wants us to look at the letter E, all right, raised to a 3.14 power, and they just chose that just to get your brain thinking about pi, I guess. So E to the 3.14 power is approximately 23 point, I think it says around to the 5 decimal places for some reason, 10387. And the other one says E to the negative 0.5 power, so E raised to the negative 0.5 power is 0.60653. So if I write down those numbers, we have, I think it was 23.10387. And this was 0.60653. Okay, so all of this is kind of leading us into what the use of letter E would be in these applications. So really, it talks about if you're looking at that radioactive decay or growth of chemical substances, and then, as I mentioned earlier, if you are continuously compounding, we're going to change our formula to be the amount at time t is equal to your principal. That's the same, but now our base is E raised to the rate times time. So let's do that same example from earlier, where we have this ability to plug in or invest $100,000. So the amount in 30 years is going to be 100,000. That's our initial amount or principal times E raised to the 0.12 rate compounded continuously, right? We're talking about 30 years. So that's why when you see this compounded continuously, we're using a base of E. So going to our calculator, we can figure out what this amount at 30 years we expect to get. So 100,000 times E raised to the 0.12 times 30 years. So $3,659,823.44. So 3 million again. 659 and then 823.44. Now, just to go back to when we did this problem earlier in the lesson, right? I'll just go back real quick. When we initially invested that $100,000 right here, compounding weekly. So instead of compounding continuously, like every moment you're compounding, if you're compounding once a week, for 52 weeks a year for 30 years, you're making $3,644,000. When you do it compounding continuously, you're making $3,659,000. So it's obviously good for us as the investor to compound as often as possible, which makes sense. You're multiplying by your interest. You're gaining yourself, or your money's making more money as you go. But it's not a huge difference in this case because compounding weekly is already a lot. All right, so it's only a difference of about $15,000. Just something that point out, yes, there's a difference, but not by a ton. Let's try this one. Notice that it's saying this radon 222 is decaying. So I'm going to use this amount at time t equals our initial amount times E to the rate times time. And the key thing here is we haven't done one yet. For decay, though, this rate is going to need to be negative, right? Because we're actually getting smaller. So the amount in 3 days' time is we're starting with 100 milligrams. We're multiplying by our base of E raised to our rate of negative 0.173 times time of 3 days. So that's just kind of one thing to notice when you see that word decay or something that's decreasing. Make sure you're using that negative for your rates. So if I plug in this into my calculator, we have 100 times E raised to the negative 0.17. Confirm. I don't feel like that's right. 3 and then times 3 days. All right, so approximately 59.5 milligrams. That's not it. 59.5 milligrams. That's how much we expect of radon 222 to be left. Okay, so there it is. That's your first lesson. Make sure you try those links. Good luck.